Okay, welcome back. This is the second Ramanujan lecture by Professor Sourav Chatterjee. So without much ado, I'll just...
So I'll assume that you are already motivated to know about lattice gauge theory, so I'll not tell you why they're important. But I'll remind you the definition in case you have forgotten. So here's a definition of lattice gauge theory in dimension D with gauge group G. So let's say D is a dimension and then G be a matrix V group. And you first define it on a finite subset of the lattice, ZD, and then you extend it to the full lattice. So suppose that for any two adjacent vertices, you have a group element UXY with this restriction that UYX is UXY inverse. And let G lambda denote the set of all such configurations, that is, attaching group elements to edges. So let this be the set of configurations. And then lattice gauge theory finds a random configuration from collection of configurations. So how is this defined? So take any square which is bounded by 4 edges. So that's called a plaquette. Let P lambda denote the set of all plaquettes. And for a plaquette with vertices going in some counterclockwise order, and given any configuration, you define UP as the product of the group elements along the 4 edges in the correct direction. And then you define an action, which is you take each plaquette, you take I minus UP, trace of that, real part of that, and sum over all plaquettes. And that gives you the action. Okay, so that's the definition. Now, once you have this action, then you define the lattice gauge theory, the probability measure. So first, let's sigma lambda be the product Haar measure on this collection, on this configuration space, and then you define this new probability measure, which is weighting this product Haar measure by this factor e to the minus beta times the action. Okay, so that's how the lattice gauge theory is defined. And so this probability measure is called the lattice gauge theory on lambda with gauge group G with inverse coupling strength beta. And then you take an infinite volume limit, so you take the weak limit of these measures as lambda goes to the full lattice. Okay? So that defines lattice gauge theory on ZD. Any questions about this definition? Okay, so that's lattice gauge theory. And also recall this definition of Wilson loops. So what are the observables in lattice gauge theory? So the interesting observables are not the UXYs, the group elements that are attached to edges. Those are not the interesting things. What the interesting things are what are these gauge invariant observables, and one class of important gauge invariant observables are these Wilson loops. So you take a random configuration from this lattice gauge theory, and then you take a loop, a closed loop with directed edges, U1 up to EM. It can be, there can be some repetitions, you don't care about that. So what you do is you take the product of the group elements along these edges, and then you take the trace of the product and take the real part of that, and that's called the Wilson loop variable. Okay? And then you define the expected value of that as the expected value under this probability measure. So that's denoted by these angle brackets W lambda. And these are the important objects in this theory, and there's this connection to quark confinement. So what we will see in this talk is how to compute such expectations approximately when n is large, and the group is SON for large n, and you have this lattice ZD, any D is fine, and beta is small enough. Okay? So this is what I'm going to tell you how this, and there's, representing these Wilson loop expectations in terms of a string theory on the lattice. Okay, that is the basic premise. Okay. So one approach to computing Wilson loop expectations is using a set of recursive equations that are now known as these Macienko-Migdal equations, or the master loop equations. These were introduced by Macienko and Migdal in 1979. And what they do is they represent the Wilson loop expectation as a polynomial in several other Wilson loop expectations. So this is what Macienko and Migdal proposed, and then the question is whether you can solve the system. Now, these equations are actually only approximate because they assumed that this expectation of a product of Wilson will be approximately factorized as a product of expectations, and this is only true it's as an asymptotic property when the dimension of this gauge group, the dimension of the Lie group that you're using, goes to infinity. So only then you can assume this kind of thing. Otherwise, it's only an approximate thing, so it's not exact. Okay. Now, if you want exact equations, so Spenta here, he derived this set of equations for this theory, and this is an exact set of equations that you can get. But stated as they are, they do not give a closed system, because when you start with the Wilson loop on the left, on the right, you do not exactly get the expectation of a Wilson loop variable. What you get is the expectation of a product of traces of a bunch of things. And so one of the things that we will start with here is that you do not take the Wilson loop expectation as your basic object, but instead you just do the following. You just take the expectations of a product of Wilson loop variables as your basic object. And if you start with that, then you can actually get a closed system of equations. Okay? So then you can get that if you take the expectation of a product of Wilson loop variables, that can always be expressed on the right-hand side as a linear combination of similar things, expectations of other products of Wilson loop variables. Okay, so this is what's the starting point in this paper that I'm going to talk about. And you will see certain things, a string theory coming out of that, and so we need to discuss that first, and which is already there in this paper. So this is the first step. So in physics, a string theory prescribes the action for a trajectory of a collection of closed loops. So suppose you have some loops, and they move through time, so they trace out some surface, and then you define an action for this surface. So we'll do something similar on the lattice. So for us, a string will be a finite collection of closed loops. So you take lattice ZD, and you take a closed loop, which may be self-intersecting. It may be traversing the same edge several times in different directions. And then a string will be a finite collection of such loops. Okay? And then we'll let the string evolve over time. And time will also be discrete, so in discrete steps. And at each time step, this components loop, there can be 4 different things can happen. There'll be a loop can be slightly deformed, or 2 loops may merge, or a loop may split into 2, or a loop may twist at a bottleneck. So, no, this let's leave that out. So that's for a more general case. But so each of these operations has 2 subtypes. These deformations, mergers, splittings, and twistings. So there's 8 possible operations. And I'll just describe these operations diagrammatically, very briefly. Okay. So here is a merger. So suppose you have 2 loops like this, and they pass through the same edge in the same direction. So this edge E, and they are both passing through the same edge E. So when you merge them, you get something like this. So this combined loop becomes like this. So you go this way, and then you continue going this way, and then you come back, and then you go like this. So that's merging of 2 loops. Now I call it a positive merger because you can merge it in a slightly different way, which is, again, the same situation. They're going in the same direction, but then when you reach here, you reverse the direction, and you come back, and then you go like this. So this edge gets deleted. Although it's traversed twice, it gets deleted. So it's the merging of these 2 loops, but with deletion of this edge. So these are the 2 ways of merging a loop. And this, you can do this if the 2 loops are traversing the same edge in the same direction. Okay. A deformation is doing this kind of merging, but with a little plaquette. So when you have a single loop, and then you take a plaquette, and you take the plaquette a variable like this, and you merge this and this plaquette, and you get this. So that's a positive deformation. Similarly, you can have a negative deformation, which results in the erasure of of edges. So you have this original loop, and then you delete this plaquette, and you get this. And the loops I'm drawing here are all 2-dimensional, but they do not have to be. They can be generally in ZD. And then you have the splittings, which is again the same loop. If there's a single loop and it passes through the same edge twice, you can split it and make it 2 loops, but without erasing any edge. Okay, so that's a positive splitting. And you can have a negative splitting, which you can have if you have a loop which passes through the same edge but in two different directions. Then you can split it in two, but you remove this edge. So you know, there are these things, and similarly you can have, you know, this twisting operation, which is you know, you have this kind of a thing where you pass through this edge in two different directions, but then you kind of twist it, and you see these two pictures look almost the same, but it's a little different. So here it's going like this and going up and going around like this. Here it's going like this and going straight and going like this. Okay, so this is kind of twisting. And there is also negative twisting, which results in the erasure of a loop. So there's 8 kind of operations. So you know, you don't have to remember all this, but just remember these 8 different kinds of operations that you can do. And so after performing one of these 8 operations, we get a new string, S prime, which may contain a different number of loops. So remember, a string is a finite collection of loops. And when you do this operation, you know, one of these loops may break into 2, which results in one more loop, or 2 loops may merge into 1, which may result in one less loop, or it may even happen that 2 merge and into nothing. So if there's a negative effect, there may be nothing, so it may reduce by 2 also. And then you just define these children that you can get from starting from a single string S. You can get starting from S, you can get a new string S prime, and there are these 8 different kinds of objects, you know, strings that you can get out of these operations. Okay, so that describes the evolution of these discrete strings. And all the possible things that can happen. So you start with a single string. Maybe it kind of keeps on deforming by adding or subtracting plaquettes, and then suddenly it splits into 2. Now you have 2 strings evolving, 2 loops evolving independently, and then each of them can merge into more, but then they can also merge back together and then cancel each other out, and you know, so it can keep happening. No, even then it can happen. If it may not have any self-intersection originally, but it may deform and keep on deforming in a way that suddenly a self-intersection appears. No, so deformation is when you add a plaquette. So yeah, you can just add a plaquette. So that's the difference between deformation and a merger. So you can just add a plaquette. You know, just take a plaquette and add it or subtract it. So there's a question of what is this action. So we'll talk about this later when we come to the representation of Wilson loops. But right now, let me present to you the master equation, the master loop equation. So consider SON lattice gauge theorem ZD for any n and any d bigger than or equal to 2 and any beta. So this is true for any beta. You take a string which is a finite collection of closed loops, L1, L2, Ln, and define phi s as a product of the expectation of the product of the Wilson loop variables for these different loops, okay? And then divide it by capital N to the power little n, and then let this absolute S denote the total number of edges. Then you can write down this equation, which is a linear equation. In fact, it's a linear system. So this phi s times n minus 1 times the length of S equals a linear combination of all these phi s primes, where phi s primes are obtained from S using one of these operations. So you have these various operations, and you have various coefficients. So if it's obtained by a twisting, depending on whether it's a negative or positive twisting, you put a positive or negative coefficient. If it's a splitting, you put in n or minus n. If it's a merger, you put 1 over n or minus 1 over n. If it's a deformation, you put in beta or minus beta. Okay, so you have this equation. Okay? So that's the master loop equation for this theory. Okay. Questions about this? Yes. So you cannot go from 0 loop to 1 loop. There is no. Yeah. I mean, you can. Yeah, sure, you can. I mean, with by adding a bracket, so you have 0 loop. But we'll not do that. So we'll 0 loop will not. But you can always go from 1 loop to 0 loop. Suppose you have a plaquette and you deform it negatively with the plaquette. So you subtract off plaquettes, then you get 0. So that will be very important for us. So we'll only consider trajectories where eventually everything vanishes. Okay, so those are the important trajectories for us for this string theory, evolving theory. So we'll see that later on.
coefficients?
No, it's all calculations. So it's just calculations, yeah. It's just calculations. So, so how is this proved? So let me just say a few words about this before going into the application. So here's a little equation, which I stated here, but it's it's known. This is the Schwinger-Dyson equations. So suppose you consider SON, consider it to be a submanifold of Rn cross n, embedded in Rn cross n, so all n by n matrices. You consider SON as being embedded in that, and let f and g be C2 functions in an open neighborhood. So the arguments of f and g are in extrinsic coordinates. So these are, so when I say del f, del xik, it's in extrinsic coordinates. So let f and g be C2 functions in an open neighborhood of SON in Rn cross n, and let E denote the expectation with respect to Haar measure. Then you get the system, this equation for any f and g. You get expectation of summation xik del f del xik times g is 1 over n minus 1 times this sort of a little more complicated thing on the right-hand side. Okay? So, so that's an equation that looks a little complicated, but it's not. It's really this equation. So, so this is just an integration by parts identity. Consider SON as a manifold now, intrinsically, and let you take the Laplacian and the gradient operators on this manifold appropriately defined, and then you get an integration by parts identity for the Haar measure, and this reduces to what you have on the previous slide. Okay, so this is just this equation. And the previous equation is just the above equation written in extrinsic coordinates, considering SON as a submanifold of Rn cross n. So this is in intrinsic coordinates, and that was in extrinsic coordinates as a submanifold of Rn cross n. Okay? No. This is just a fixed equation. So the proof in the original paper, what I had, I did different proof, but this kind of simple interpretation was communicated to me later on. However, this extrinsic coordinate version, which is much more ugly than what I wrote here, is important for calculations. So this is used for calculations. Okay. So how do you use this? Let L be a loop and E be an edge of L, and take the matrix UE attached to the edge E, and let denote its ijth element by Qij. Let M be the total number of occurrences of E and E inverse. E inverse is the edge in the opposite direction in this loop L. Okay? So then one can show that M times the Wilson loop variable WL is summation Qij times del WL del Qij. Okay? And this is very simple. This is because WL is a homogeneous polynomial of degree M in the Qij's. Okay? And if all the other matrices are held constant, and whenever you have a homogeneous polynomial of degree M, you have this identity, that summation xi del p del xi is m times the polynomial. Okay? So it comes from this. So you have this representation. And now how you complete the proof is the following. Let S be a string, which is a collection of closed loops. Now take any edge E of the first loop, L1. Let M be the number of occurrences of E and E inverse in this L1. And denote the ijth element of UE by Qij. And let G now be the product of these Wilson loop variables WL2 to WLN, excluding WL1, and the probability density of SON lattice gauge theory. So consider now SON lattice gauge theory on a large box, not on the full lattice. So there is a probability density. So you take the product of the probability density and these Wilson loop variables, let that be G. And let F be this WL1. Okay? So then M times the Wilson loop the expectation of WL1 through WLN. So this is expectation in lattice gauge theory. This is expectation with respect to Haar measure. So write the expectation in lattice gauge theory as expectation in Haar measure of WL1 times G, where G is this object, because you're taking the probability density inside G. And then using the previous identity, we can write it like this. And then one can apply the lemma to this side. Okay? Just apply the lemma. And then a whole bunch of calculations, but it turns out, a little miraculously, that the result that you get, it has no reason to be, but it just turns out that the expected value, the result is the expected value of a polynomial in Wilson loop variables. Okay? And this is where you get all these things coming out, these splittings and mergings and twistings and so on. So everything comes out from here. Okay? And this is irrespective of how many loops that you have. And then what you do is you average over L1 and E. So arbitrarily, we took the first loop and some arbitrary edge E in there. So now you average over all loops and all edges, or sum over actually, all loops and edges, and you get the equation that we have. So, you know, this is a derivation of this equation. And the fact that the interesting thing is that you get tractable objects on the right-hand side, you know, so objects which are similar to this. Okay. Here are the remarks. So the 8 string operations that I wrote down, they arise naturally from this calculation. You know, I didn't guess those. And there seems to be no particular reason why this should happen, except that it just happens. And you know, as I said in the beginning, that you know, Spenta has this paper where you start from this Wilson loop expectation, you can write down, and the similar kind of operations come in. And Jafarov, who's a former student of mine, worked out these equations for SUN theory, and it's a little different. The operations are a little different. Now the question is, you know, why does this keep happening? And is there a general way to see that this will happen for general Lie groups? So that's, I don't know whether that's true or not. Yeah, some other operations. So there is a different operation that comes in for this. Yeah. Now, these operations look kind of delicate, that there are 8 different kinds, but what I think, you know, so I haven't been able to extend this to a continuum setting, but if you go to a continuum setting, they will all reduce to some fewer kinds of standard operations. I don't think, you know, there'll be so much, you know, delicate. Okay. So now let me talk about the large n limit. So this I think started with Tufts' work, where Tufts looked at high-dimensional gauge groups such as SON or SUN with n going to infinity, and this is known as large n gauge theory. And one of the reasons for taking n to infinity is that it simplifies many of the calculations, so you can kind of do some approximate calculations. And this work pioneered this theory of planar diagrams, and there are these connections with random matrices. So let me talk very briefly about planar diagrams. So this talk doesn't have much to do with planar diagrams, but let me just tell you the background since we are talking about this. So recall from the first lecture that in quantum field theories, there are certain, we do perturbative calculations, okay? These perturbative calculations are handled using Feynman diagrams. So there's a stellar expansion kind of thing, and then you, to keep a handle on what you're doing, you use this diagrammatic approach. And Tufts realized that for gauge theories, you can modify this Feynman diagram method to convert these diagrams into surfaces with edges, vertices, and faces. So this you can do. And then Tufts suggested that if you replace the parameter beta by n times beta, so it's just a rescaling, you get something nice. So what you get is that when n is taken to infinity and beta is varied like this, the coefficient beta is replaced by n beta, you can actually get a perturbative series expansion in powers of 1 over n. So this is called the 1 over n expansion, and it's a well-known thing. And then you can get the terms in the expansion as sums over surfaces. So the kth term will be a sum over surfaces of genus K, so this is the beginning of this planar diagram theory. Now, there is a long history of planar diagrams in mathematics also. So there is a large body of random matrix literature by Alice Guione and co-authors in probability, and there are other works in other areas. So it has inspired a lot of things in math, so I'll not go into all that. However, originally, physicists wanted to work with, wanted to understand gauge theories, and I don't know of a mathematical work which deals with the planar diagrams from gauge theory, so I haven't seen any papers on that. So let's talk about lattice gauge theories now again in the Tufts scaling. So recall that you have a string S, which is a collection of loops, and phi n of S, so now I'm putting a subscript n, is this expectation of a product of Wilson loop variables divided by n to the n. And here expectation with respect to SON lattice gauge theory on ZD. And suppose we replace beta by n times beta. Okay? We take the Tufts scaling, we replace beta times by n times beta and send to n to infinity. The question is whether does this converge to a limit. So if n is large, can you approximately calculate phi n of S? And can you calculate that? So note that this is always bounded by 1 because these are traces of n by n matrices, unitary matrices. And so these are all bounded by capital N. And so therefore, when you divide by capital N to the little n, you get something bounded by 1. So remember, capital N was a dimension of the matrices. So these are n by n matrices. And little n is the number of loops that you're taking. So this thing is always bounded by 1. And there are only countably many strings. Okay? So these are all finite closed loops, so there are countably many strings. So by a subsequential argument, you can always show that there is a subsequence along which all these things converge. Now, whether they actually converge, overall. So let phi be a subsequential limit simultaneously for all strings. Then one can see from the master loop equation that this limit must satisfy this simpler equation. Okay? So note that only splittings and deformation survive. The other terms, the n is such that they go to 0. So in the limit, there is a simpler equation that is satisfied. So as I said, the twists and mergers have disappeared. And this holds for any beta. Again, this equation holds for any beta and any subsequential limit, okay, of these objects. Now, if this system of equations has a unique solution, then we may conclude that the phi n's actually converge to this limit. Okay. So one has to show that this system of equations, note that this is a system of equations over all strings. Okay? And the question is whether this has a unique solution. And if it has a unique solution, then we may conclude that there is a limit. So what I showed is that this limit, this system of equations indeed has a unique solution when beta is sufficiently small. And therefore, phi n converges. So here's an open problem. Show that the limit exists for any beta. So I don't know whether this is true, possibly, but no. Okay, so Spenta says no, so it must be no. Okay, so then show that. Okay. What? There may be phase transition. Okay, so then the new open problem is show that there is the limit does not exist for large beta. Okay, so okay. Okay, so here's a sketch of the proof. So there's one more result. So I have this, and then there is another result which says there's this gauge string duality. But before going to that, let me tell you the proof of this result. How do you show that there is a unique solution of the system? Because it seems like a complicated system. How do you show that there's a solution when beta is small enough? So suppose phi and psi be two solutions of the master loop equations. Okay, so let me just show you the master loop equation one more time. Here is this equation, the limiting master loop equation. So this phi is a functional defined on all strings. And then you say it satisfies this equation, and the question is whether there is a unique solution. So let this be two solutions. Let delta be the set of all finite sequences of positive integers. And if you have two such sequences, we say that one is dominated by the other if the two sequences of the same length, and delta prime dominates delta in each component. Now, for a string S, let delta S be the lengths of the components. So the length of L1, length of L2, length meaning number of edges counted by multiplicity. And for delta, which is a finite sequence of positive integers, let D of delta be the supremum over all strings so that delta S is dominated by delta of phi S minus psi S. Okay? And it like this. And there is one other important thing, which is for any sequence of finite integers, define an index as a sum of the integers minus the number of integers. So n can vary. So you see the sum of the deltas minus n. So you define this index. And finally, for lambda, for a number lambda between 0 and 1, define f lambda to be the sum over all delta in this big delta of lambda to the power the index of delta times d delta, where d delta is this. Okay? So d delta is defined using phi and psi. So you define this number. So it's upright. It's not clear whether this is finite or not, but it's an infinite sum of positive things, so it is either finite or infinity. So you can always define this. Okay. So you define this object, and then you show first thing is that f lambda is finite if lambda is sufficiently small. So you take this, and then you show if lambda is sufficiently close to 0, then this is finite. And for that, you just use that this phi and psi are bounded by 1. And then this, do a counting argument. So you can do a counting argument to show that this is finite, if lambda is sufficiently small. And then what you do is you show that the f satisfies a recursive inequality. So you use the master loop equations now. So you have this phi and psi in this definition of d delta. So again, sorry, going back, you have this d delta here, and you have this phi and psi. So use the master loop equation for these. So you assume that phi and psi both satisfy the master loop equation. So use that, and then you see how this index changes, this iota of delta, this changes as you do a splitting or merging or whatever, all these other operations. So using that, you can show that f satisfies this kind of an equation, this kind of an inequality. Prove that. And from this, you see that if first you choose lambda small enough, and then you choose beta small enough, depending on both lambda and d, then you can make this coefficient less than 1. Okay? And this shows that f lambda must be 0. So therefore, if beta is small enough, then it follows that phi must be equal to psi. If f lambda is 0, then phi must be equal to psi. So although you have this complicated system of equations, you can end up showing that if beta is small enough, then it has a unique solution. And therefore, these phi n's must converge to this unique solution. Any questions? Yeah. 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 Oh, yeah. So yes. So let me go back to that. Back a long way. Yeah. Okay. So recall that there is an n minus 1 here. So when you divide by n minus 1, these two go away. These two obviously also go away. These two remain. Yeah, beta is replaced by beta n, and so beta remains. Yes, I'm coming to that. So, okay, so here, gauge string dualities, I'll just recall from the last lecture, duality between, well, as I mentioned, duality between SON lattice gauge theory for large N and lattice string theory was established in this paper, and it may be the first rigorously proved gauge string duality, but I'm not 100% sure. So let me now state that result. So in this lattice string theory that I defined, call the trajectory of a string vanishing if it vanishes in a finite number of steps. So you start with single string or multiple strings, and then you let them evolve, and we say that trajectory is vanishing if it completely vanishes after some stage. So once it vanishes, it cannot come back. So we'll not allow that here. So let x equals S0, S1 up to Sk be a vanishing trajectory. The action of x is defined as W of x is the product of these individual steps, WS0 to S1, WS1 to S2, WS minus 1 to Sk, where these transition weights are defined in the next slide. Okay? So it's just like when you're doing a Markov chain, you have these steps taken by a Markov chain. The probability of the trajectory is the product of these individual probabilities. So it's just like that. You have this product of these individual steps. However, here the difference with the Markov chain is that here the W will not necessarily be non-negative. Okay? So it can take positive and negative values. So that leads to some complications. So here is the weight of a transition. So let S be a string and absolute S be the total number of edges counting repetitions. And if S evolves into S prime after an operation, you define the weight of this transition as minus 1 over the length of S if S prime is either a positive twisting or a positive splitting or a positive merger, 1 over the length of S if S prime is a negative twisting, negative splitting, or a negative merger, and minus beta over the length of S if S prime is a positive deformation, and beta over the length of S is if S prime is a negative deformation. Okay? So these weights come from the master loop equations that I wrote down. So they arise from that, so they're not, not guessed. So they come from the master loop equation. As I said, the important thing is that it can both be positive and negative, so it's not exactly like a Markov chain. And the action of a vanishing trajectory is computed by multiplying the weights of the successive transitions. So here is where the vanishing trajectory is important. If you have non-vanishing trajectory, you don't know how to define this, so you just define it for vanishing trajectories. Okay, so here is the main theorem. So consider lattice gauge theory, SON lattice gauge theory in ZD with coupling parameter n times beta, or inverse coupling parameter n times beta. Let S be a string and let phi n of S be the product of these Wilson variables, the expectation divided by n to the n. Then if beta is small enough, small enough depending just on the dimension d, yeah, just that. Okay. Then you have this limit, the limit which we showed that it exists, but it's given by the sum of, you take sum over all vanishing trajectories in the string theory. So this lattice string theory that we find, you take script x of S to be the set of all vanishing trajectories starting at this given string S, okay? Whose steps consist only of splittings and deformations. Yes, I should have mentioned that before. But so right now, we don't need mergers and twisting. So you only consider vanishing trajectories whose steps consist only of splittings and deformations. So splittings means splits into two, and deformation means you just add or subtract a placket. And Wx is of this trajectory, which is the product of these weights along this. So this Wx can be positive or negative. But the sum, which I showed, is this is absolutely convergent. If beta is small enough, this sum is absolutely convergent, and it equals this limit. Okay. So that's the main result of this paper. Ooh. I didn't try to optimize that. No, so small enough here just depends on dimension d, because n is going to infinity. The beta small enough doesn't depend on little n also. So it's just, it's a result that works. So it just, I should have said that. Beta small enough just depends on dimension. Everything else is. Yeah, so I'll talk about the proof a little bit. So yeah, I'll talk about the proof. Okay. So the condition that trajectories can only have deformation and splittings and no mergers ensures that the surface traced out by these trajectories have genus 0. Okay, so if you allowed mergers, if you allowed trajectory to split and then merge back again, that would have, the kind of the discrete surface traced out by trajectory would have higher genus, but we don't allow that. And that's because we were only talking about limit. So with Jafar, so we have this full 1/n expansion, and the higher order terms have these trajectories that trace out surface of higher genus. So the kth order term will allow k mergers. Okay, that's how it comes about. It looks similar to this planar diagram thing, but it's actually, these are different things. So this is, these works look at perturbative expansions in the continuum theory, whereas this is a non-perturbative theorem for lattice gauge theories in discrete setting. And this planar diagram approach typically gives the result in the form of a divergence series, whereas here you have a guarantee of convergence. So there, it's different, but it's interesting that similar things come up. You have this kind of discrete surfaces of higher genus when you have, So also, if you're familiar with how planar diagram theory is derived, it's quite different. So it's you consider for large beta, you consider the theory as a perturbation of a Gaussian theory, and that from that you get this, and this is very different than that. Okay, so here's a proof sketch. So how is this proved? So for a string S, you define index similarly as before. You take the sum of the lengths of the individual loops minus number of loops. You define this index, and then what we prove various things for strings by induction on this index. So the key step is that if you obtain S prime from S using a splitting, then the index decreases strictly. Okay, this is always true. Whenever you do a splitting, be it a positive splitting or a negative splitting, the index must decrease strictly. So that's what allows us to do the induction. So then what we do is we define a collection of coefficients ak of S. So these are indexed by non-negative integer k and a string S. And the definition is inductive. So we take induction on k and simultaneously on this index. Okay, so there is a two-way induction we define this thing with these two properties, so that for beta sufficiently small, this sum converges, absolutely, for any string S. Okay? And the function phi satisfies the master loop equations. So we define, this is the guiding principle for the definition of these coefficients. So we define these coefficients in such a way, using induction, that using the inductive definition, we can show that this is convergent if beta is small enough, and it satisfies the master loop equations. Okay? And then these two properties and the uniqueness of the solution of this master loop equation shows that this must be the limit. Okay? So we do not arrive at this thing, we just guess it. So we just guess the inductive properties that AK this. So first of all, you assume that your limit phi has a power series expansion like this. So the phi s, the limit phi s is a power series in beta where the coefficient depends on s. And then looking at that, you just guess, what kind of recursive relation the coefficients must satisfy. And then you define the coefficients in that manner. You using this concept of the index of a string, you show that these AKs can actually be defined inductively. So if you have a computer, you can write a program that defines these AKs inductively. Okay? So you can do that. And when you have this definition, since it was derived a priori with the knowledge of the master loop equation, you can show that this thing will satisfy the master loop equation, and by the uniqueness theorem, you show that this is the correct limit. Now, then what you do is you take for any k and s, let xk of s be the set of all vanishing trajectories with only deformations and splitting, which start at s and have exactly k deformations. And then you show by induction, again on k and s, again the induction uses simple induction on k, but this index induction on s, this two-way induction, you show that this term aks beta to the kth term in the power series, is actually this sum over trajectories like this. So here, trajectories is not over all vanishing trajectories, but all vanishing trajectories with only deformation and splitting, which have exactly k deformations. Okay. Okay. So this is actually only a finite number of trajectories like this. So you can show by induction that this identity holds. Using the definition of AK and using the definition of the weights, you can show by induction. So it's all this two-way induction. Okay? And as soon as we have this, it follows that you have this identity. Okay? And the absolute convergence requires a different argument, so I'll omit that here. It's basically the same. What you do is, instead of AK of S, you take BK of S, some other coefficient, where BK of S times beta to the K is the, so BK will be the absolute value, and then it will satisfy another system of equations, and then you can show this. So it requires a different argument. Okay. So that's more or less the proof. Okay, but there is details, but which I haven't shown. So here are some open problems. It's very important to develop a continuum version. So Spenta has a discussion of that in his paper on the continuum version, what should be, but I have no idea how to do that. Yes. In terms of beta. Yeah, so the thing is, here, the result that I've presented, is just the first term in the 1 over n expansion. And here, beta just depends on d. So it's some dependence on d, and one can try to be more explicit about that. The more interesting thing is when you have the 1 over n expansion, and then you have up to the kth term, 1 over n. So then that holds for small enough beta, where small enough now depends on k and d. And so how it depends on k, and we got very bad things, probably not satisfactory. So something like e to the k squared or something like that. So that's, yeah. Yeah. Yeah, so we have not actually proved that the series converges for a finite n, even if it's large. So the result is about the limit as n goes to infinity. So if you send n to infinity, you get a limit, and that's a power series in beta. But if n is large but finite, we don't know how to get a convergent expansion. For that, we only know if you want up to the kth term, okay, I can give you up to the kth. But it's only an asymptotic series expansion, so we have not been able to do that convergent expansion for finite n. So, okay, so continuum version of these results. So you can look at Spenter's paper for what can be a candidate for a continuum version of these results. Or even if you are not able to do it, at least develop a version for large beta. So that's the first step towards the continuum version. So there are results of Basu and Ganguly which show that you can do exact computations. So this sum over trajectories is okay, so I gave it to you, but it's a complicated thing, right? Because there are so many trajectories. And one of the technical challenges in this work is to prove that this convergence happens because number of trajectories grows very fast, like e to the k squared, or I don't remember, but certainly not easy to establish this convergence. But it happens due to certain cancellations. Now, the question is whether you can actually do this calculation in some and get meaningful results. So this was done in 2D using very nice combinatorial connections and free probability theory in this paper. So this the sum over trajectories that you have, and the question is whether one can extend these results to higher dimensions. One can start from this. Whether one can start from this string theoretic representation that I showed you and get more information about these objects. Okay. Well, as I said, okay, so Spenter says that there should not be a limit, so okay, so maybe no limit for large beta would be great. I mean, showing the phase transition, so phase transition. So in fact, in 2D there is a phase transition. One can show this from these exact results, and there are of Gross and Witten for 2D UN theory, but prove the existence. And there are some more problems that I have in the preprint. So. Okay, so that's all. Thank you. No, so ZD. Yeah, no, so you can make it whole of ZD. So the master loop equation that I showed depends. The calculation is done using a finite box, but it doesn't appear in the equation. So as long as the box is large enough, the same equation is true. So therefore, you can take the box and get the same equation for any weak limit.
So I'm guessing many of the questions you talked about are fairly old, right? I mean, they've been around for a few decades. So I think I missed what is the new perspective or idea or development that has taken place that has enabled this progress that you described?
So the thing is that the reason that it's old because people, I think on the mathematical side, people stopped making progress. Okay. So anything new that you can say about these things would be interesting. And understanding lattice gauge theories and the limits, as I said, the Yang-Mills existence problem, these are all interconnected. So understanding lattice gauge theories would be a big step towards that. So any kind of understanding that you can get about these things, or about these four general classes of open problems that I mentioned in the first lecture. So these are all interesting and relevant. And if anybody makes any kind of progress, activity will become more intense.
I guess my question is, so what enabled the progress that you described? I mean, you described some results. I mean, what is the sort of new, why could this not have happened 10 years ago or 20 years ago? Are there some new techniques that have been developed in probability theory, or is it just that nobody tried to think about it in this way, or what is the...
Yeah, that's a hard question, what to say about that.
So it doesn't fit into some larger context of recent developments in probability theory or something?
No. So there have been, so for example, there was this talk this morning by Fanny Algeri on this nonlinear large deviations, and And there was, there was no result until there was something, and that happened. So.
I think I should make one point over here, actually, that since this is a math talk, that the Migdal-Makhenko equation is actually not correct. As you know, that they missed out the string rearrangement terms are not there in their paper, actually. And they are very important, actually, if you go to lower dimensions to be able to work out.
Yeah, I saw that in your paper, but I was not courageous enough to mention saying they're wrong.
Yeah, okay. Yeah. So his Migdal's argument was that these terms go away in the right type of regularization, and regularization should serve physicists and not the other way around.
I see. There are things like in the first lecture, there was this work of Balaban, this famous work they mentioned, long papers, and what I couldn't mention was not courageous was that nobody can read those papers. So there are things that I cannot say, but yeah. Yes.
So when n is finite, not tending to infinity, you have to consider higher genus surfaces, not just vanishing trajectories, but
yeah. So when n is finite, the kind of result that you can get is that phi of s becomes some phi 0 plus 1 over n times something plus 1 over n squared times something plus 1 over n to the k times something. But if you keep on expanding, you cannot show convergence. So what you can tell is that plus order of 1 over n to the k plus 1 as n goes to infinity. That's all you can say. So for any fixed k, you can have a result like that. Okay? But you cannot have a...
But you have not just vanishing trajectories, you have to consider all possible
Yes, so for the kth term, you have trajectories which are allowed to merge k times.
Yes. Okay.
Yeah, that allows k handles. For how small is beta? So in the n going to infinity limit. So beta is just something beta less than beta 0 depending only on d, on the dimension d of the lattice. So there is no other, yeah.
Probably a function of d?
Probably, probably things get worse. So because the convergence thing that I showed, the coefficient in front of f was larger for larger d. So you'd need smaller beta for higher dimensions for this argument to go through. Yeah, but okay.
So for finite n, now that you have your system of equations for these loops, a string, whatever, can you show something like if I have two loops which are far away, their expectation values is like the product of their something like a mean field.
Yeah, so okay, that's a good question. So what I didn't mention here is that there are some uses of this string representation. Using this, for instance, you can prove the factorization property in a large n limit. So in a large n limit, you can show that the expectation of the product of two Wilson loops is the product of the expectations, using this representation.
For finite n?
For finite n, I don't know. So, for finite n, even proving the decay of correlations, I don't know if it has been proved. I mean, for small beta, certainly. For small beta, you can have general techniques by which you can. But for large beta, I'm not sure. And here, beta is replaced by n times beta. So, yeah, so I don't know exactly.
Oh, no, I meant your first result where you have fixed n. And
yeah, no, yeah, so for finite fixed n, you can prove decay of correlations for small beta, but for large beta, I don't think it has.
Okay, that's what seems to be happening here, right?
Yeah. Yes, that one can do because in this later work with Jafarov, we have error bounds for this limit. Okay, so this, when you have this convergence, so phi n s minus phi s, the difference is of order 1 over n. You can show this, where the constant will depend on the string and various other things. So since you have the factorization for the limit, you will have factorization up to order 1 over n for 2 loops. Yeah, that's right.
Do you see any role for free probability theory in, you mentioned in this work in 2D, but in these general higher dimensional cases, do you see that in any sense appearing in these equations?
Well, it's a much better person to answer is back there, Shishant and Riddhi Pratim, they'll be able to tell you in much greater detail, what, yeah.
Yeah, but in your equation, is there any sense in which your equations could be recast very naturally in
that would be great. I don't know. I don't think it has been done, but if possible, that would be very nice to be able to do that. But there is a possibility, and since there is this two-dimensional work, so the possibility that.